3, 2, 1, here we go. Welcome to Math 267, Ordinary Differential Equations with Laplace Transforms. Let's get going. Alright, so our goal for our very first video is to basically just establish the goal of the course and the basic terminology we're going to be using throughout the class. Okay. So, what is this class all about? Introduction to Differential Equations. Okay? Well, the good news is, this course is singularly focused, right? So this might be the first math class you've taken in a while where we've just got one thing and one thing only on our mind, and that is solve differential equations, right? In calculus, we kind of learn a whole bunch of techniques involving derivatives and integrals and how they interact and, and how they're used to solve various problems, and, right, those courses can sometimes feel like there's all sorts of weird, like, left turns that sometimes you make, but not for us. So that's one benefit. We're going to focus on one thing, and that is, how do we solve differential equations? So obviously, the first thing we want to do is ask, alright, well, why? Okay, we're here, we're in this class, why are we here? Other than your program is requiring you to take this course. So why? Why is this course a thing? So the main reason this course is a thing is that pretty much every single physical phenomena is a differential equation. You see a bird flying? Differential equation. Right? You drop a pencil? Differential equation. You put something in the oven? Differential equation. So all of physical reality can be modeled in terms of differential equations. Now, right, of course, that's the human experience coming into play. Birds probably don't compute differential equations to fly, but our perception of reality, we can use differential equations to explain those sorts of behaviors. Okay, so they're very pervasive in the physical sciences. And from a mathematical standpoint, as we're going to see as we go on, the techniques and methods that we're going to use to solve differential equations and investigate and study them, first of all, will show up a lot in other math courses and other things that you may be pursuing. And on their own, they're all very intriguing. So as we go forward in the class, we're going to learn a whole bunch of stuff. And you know what? It's fun. I have taught this class multiple times over many years now, and this is absolutely, to me, the class I think is the most fun. Definitely because of the first point too, because a lot of what we're going to talk about, there's a direct link to where it came from in terms of problems people were looking at, right? So I've already mentioned, heating and cooling. We'll look at the classic mass spring and some other fun differential equations along the way. Okay, so that being said, what exactly is a differential equation? Well, an equation with a derivative. The name is not misleading. So here you go. There's a differential equation. Right. Now, note some things about it in this expression that I wrote, and especially this line right here that I put in bold. Right. You can read this. Right? When we read this, specifically, this is telling me that the derivative of y with respect to x is equal to 2x. So I've communicated a whole bunch of information to you very concisely and very precisely with our wonderful mathematical notations. Right? Mathematics, in its own right, is a language, so it's got grammar and all that other fun stuff. Right? In this very brief equation, I've communicated a bunch of information to you. I have a function y depending on a variable x, and I told you some information about my function. I told you its derivative is twice x. All right, and before we even get into anything, right, immediately your calculus brain should be activating, and you're immediately thinking of, ooh, I want to integrate both sides, and tell you that y has to be x squared plus c. Good stuff. Right. We'll get more into that, but for right now, let's just focus on reading these equations on their own. Okay, here's another example, very similar, but distinctly different from this equation right here. It may look at first glance that there's not too much different here, but this equation is communicating something completely different. So again, read the equation. Right, this first one, the derivative of y with respect to x is twice x. Here, the derivative of a function y is twice itself. All right, and as we're going to see, these two equations have wildly different solutions. All right, so as I've kind of already let slip, the solution to that one is x squared plus c, and the solution to this one we'll see in a little bit. Now, note this notation hides the independent variable, so the variable the function depends on. The unknown function is sometimes referred to as the dependent variable. So this notation specifically is the Newtonian notation, or the notation that Newton used when he was talking about derivatives. And while it has some benefits, one of the disadvantages it has against the Leibniz notation, which is this notation up here, is that it obscures the independent variable. That allows us to choose whatever we want. So when we write an expression of this form, y prime equals 2y, I have a function whose derivative is twice itself. The variable of the function can be chosen to be whatever we want. Typically, we'll pick x and t. Sometimes we'll pick theta. But for the most part, that's what we'll do. Okay. So, there we go. We've already started to unpack a lot of stuff here. All right, so let's keep going forward. So, when it comes to differential equations, there are basically two types. So the first kind is an ordinary differential equation, and this is an equation where the derivatives and the functions only depend on a single independent variable, such as this one right here, which again we can read. My function's second derivative, there's the notation for the second derivative in Leibniz notation, my function's second derivative plus 4 times itself equals 0. Okay, so again, exactly what I'm doing right there is something you really want to get in the habit to, especially in this class, because a lot of times just reading out loud what the equation is saying will tell us how we can go about finding solutions. Okay, now these types of equations right here are the ones we're going to focus on in this course, and specifically this equation. Oh boy, we're going to spend some time with this one. So again, differential equations, model physical phenomena. This one right here, this is a good one. We'll get to it. All right, so this is our realm. We're going to study equations with derivatives, and we're only going to have the functions depending upon a single independent variable, and that tells us that, well, there's probably another branch of mathematics, and these are the partial differential equations, where you look at equations where your functions, your dependent variables, actually have multiple independent variables. So if you've taken Calc 3, not a prereq for this course, but we'll dabble with it in and out. So if you've got a function with multiple variables, you can take their derivatives, and you can look at equations thereof, and these is the realm of partial differential equations. Specifically, I have an equation u with two variables x and t, and I'm told that its second partial with respect to the variable t coincides with its second partial with respect to the variable x. Right, this is actually an example of what is known as the wave equation, and most physical phenomenon are not only just spatially dependent, so x, but also have a time dependency t. So if that sounds cool and interesting, then once you finish with this class, well, then I got a class for you. Math 385, partial differential equations. All right. Okay, so we'll leave it at that, but we'll come every so often and talk about partial derivatives specifically. So if you've taken Calc 3, you know what's going on here. If you have not, don't worry about it. Anything that we need, we'll spell out in a lot more detail. But yeah, so our goal is ordinary differential equations. Okay, so for any ODE, the first thing we want to know is its order. And by order, I mean how many derivatives are showing up. So, for example, dy dx equals 2y, function whose derivative is twice itself. This is a first order differential equation because the highest derivative that I see is a first derivative. First order, insert a Star Wars joke here. Rise of Skywalker. Boom. Roasted. Alright, now here is a second order differential equation, right? So we've got, this one's a little bit more of a mouthful, but I have a function whose second derivative times 1 minus x minus its first derivative times 4x plus 5 times itself coincides with cosine. And note that the highest derivative that appeared was the second derivative. Okay, so we are going to first attack first-order DEs in this class, and then we'll move on to second-order DEs. But you can obviously go higher. And we want to be careful, especially when it comes to notation, because it's very easy to get lost in notation. Right? It's the one flaw mathematics has. We got philosophy beat, right? Because we all agree on definitions. We don't spend all of our time arguing about, well, what is a derivative? Right? No. We've agreed on what a derivative is. The thing we fight each other about is what notation should we use for it. So that's where that's the mathematician's trolley problem right there. I don't like your notation. But anyway, so this is a third order one. A third derivative appears here. This derivative is being raised to the fourth power. So in other words, this right here is the derivative times itself 4 times. Okay, and now this one is something we can read as well. I have a function y whose third derivative times x minus itself times itself 4 times, or itself raised to the fourth power, plus itself equals 0. Okay. Now, in most physical applications, first and second order ODEs usually do the job. There are the occasional higher order ones. When we start talking about higher order DEs, we'll talk a little bit about that, not to spoil anything, but excuse me, when you attach a beam to a wall and push down on it, that's a fourth order DE, apparently. The Hubble telescope used a fifth order DE when they were designing it, if I remember right. But and you can imagine we can go even higher and have a 12 billionth order differential equation. But for most purposes, lower order DEs usually do the job. Okay. Now, the other aspect of ODEs that we care about, once we've got an order figured out, the next thing we want to look at is if it's linear or nonlinear. Okay, and we want to be really careful about what these words mean. Obviously, linear should be conjuring up lines in your head, but it's not exactly a line. So, here's a not fully precise definition for what linear means, but the definition I like. Linearity for a differential equation will mean that the dependent variable is going to be affected by things, right? There's going to be an equation involving our unknown function, and our unknown function is going to have stuff happening to it. We've already seen it being multiplied by 2, it taking a derivative, taking a fourth power of it, putting it inside of cosine, things like that. By linear, we are going to restrict the equation to only do 3 things, and that is scale, add, and take derivatives that are with respect to the independent variable. So the dependent variable can only be affected by scaling, adding, and differentiation with respect to the independent variable. So for an example of one, t squared times y double prime plus 6y equals cosine of t is a linear differential equation. Okay, so let's unpack my little definition here and why this satisfies it. Okay, so here we see y is being scaled. Okay, so my unknown function being scaled, good news. An addition, okay. Derivatives, respect to the independent variable, right, 2 derivatives of y here. Note I'm using the Newton notation again, although we do know what the independent variable is. By context clues, it's t. Now note, the second derivative is being multiplied by something. However, the thing that's multiplying it only involves the independent variable, so it's not really a multiplication, it's really a scaling with respect to the independent variable. There we go. And here we have a cosine, but there's no thing involving our dependent variable, it only involves the independent variable. So, for something that's nonlinear, take the exact same equation and replace the t with y. This has now become non-linear because an operation that is affecting my dependent variable goes outside of the realm of scaling, adding, and derivatives, right? It's now cosine of y. And as we're going to see, this equation right here, I know how to solve this, right? In this moment right now, I've got a pretty good idea of how to solve this. This thing right here, I legitimately have no idea what the solution to this thing is. I can put in the Wolfram Alpha and it's going to give me something, but I've got beyond me the techniques that it's going to use, right? And this is going to represent a huge dichotomy in ordinary differential equations and effective differential equations in general. If things are linear, things are nice, and we know how to solve them. And in fact, we're going to focus mostly on linear, higher-order differential equations. The nonlinear ones, forget it. Now, if you want a really precise definition, because like I said, the benefit in math is that we have nice, precise definitions. Precisely speaking, an nth-order linear differential equation is anything that can be written in this form, right there, where the a sub n's and the f are functions that depend on the independent variable t, and y, of course, are my unknown functions. So basically, if you take a look at this and really think about it, kind of looks like a polynomial, right? You've got your powers, yeah. You've got your constant term. You've got your coefficients. Ooh, alright, okay. I wonder if there's some humongous, deep, meaningful connection between linear differential equations and polynomials. I have no idea. I haven't taught this course before. Alright, we'll see. Okay, so, that being said, now that we've gotten a taste for different types of differential equations and the kinds of classifications we're going to do for them, sorry if you're hearing noises, I'm recording this video down in my basement, so yeah, might be some strange sounds going on. Alright, now that we've discussed the types of differential equations that we're going to encounter and play with, we now want to start asking, well, how do you solve these things? Okay. Well, before we talk about how we solve them, let's talk about what solutions are going to look like. Okay. So this way, when we see one, we know what it is. We go like, that's a solution. Right. That's a good thing to have ready to go when we're trying to find them, if we know what they look like. So by an explicit solution, we're going to mean just a specific function that will satisfy the equation. So, for example, the function phi, defined by 7e to the x, is an explicit solution to y prime is equal to 2y. Right, the function phi, its derivative, is twice itself, and that can be easily verified by taking the derivative. Right, chain rule spits out a 2, 7 goes along for the ride, derivative of e to the x is itself, so boom, there you go. That is an explicit solution. That solves the differential equation. Because if I plug it in, it satisfies the relation. Now, for this one, I want to note notationally again, the pitfall of mathematics. I used phi here to make it clear what's going on. A lot of times when we talk about solutions, we will say y is equal to this and say that it satisfies the equation, and it's kind of on you to recognize that we're technically talking about two different y's, but you'll get used to it. I'll ease you into it. Okay, so that's an explicit solution, so there's probably another side of the coin to that, and that is the implicit solution. And this means that what I have is not a function that solves the differential equation, but rather a relationship that the variables have to have. So, for example, this equation right here, y squared minus y cubed equals 8, is an implicit solution to the differential equation dy dx is equal to 3x squared over 2y. So in other words, my function y, its derivative, coincides with 3x squared divided by twice the function. So it turns out that I can't exactly give you a formula for this function, but I can give you a relationship the function has with its independent variable x. Specifically, my function, squaring it minus x cubed gives me 8. And now if you wanted to, you could of course add the x cubed over, but now solving for y brings in square rooting, and that brings in all sorts of problems. So there are a couple of differential equations we're going to run afoul of where we're not even going to attempt to get the actual formula for the function, because the formula, the formula will be worse. So let's just get this and call it a day. Right. Now, how do I know this is actually an implicit solution? How do I know that a function that satisfies this condition solves the differential equation? Well, the name should be giving away to it, because you may not notice it, but your brain does. We've seen the word implicit before. If I implicitly differentiate this equation right here, Note, y is a function of x, so when I take its derivative, chain rule applies. And then I solve for dy dx. Ooh, look. Ha ha ha. Divided over, we've got the solution to the differential equation. Nice. So, there we go. We're going to encounter this every so often. Most of the equations we deal with we'll get explicit answers for, but there are going to be some where we'll be happy with an implicit one. And this happens a lot, and we'll talk more about this, that even though we can solve a good number of differential equations, sometimes the solutions don't have a reasonable closed form, and we'll accept something like this as an answer and just kind of, wash our hands and walk away. All right. So, while we're still on the topic of solutions, now that we have the distinction between explicit and implicit, let's talk about something that maybe jumped into your head. Speaking of calculus, we know that when it comes to derivatives, undetermined constants are going to play a role, right? If two functions have the same derivative, that doesn't mean they're the same function, but at worst, they differ by a constant. So when we try undoing derivatives, we should expect a constant to show up, basically saying that, well, I undid a derivative. Differentiation does not uniquely determine things, but it does determine things uniquely up to a constant. So, let's revisit my favorite differential equation, y prime is equal to 2y. Our experience from calculus tells us that we know what the solutions to this must be. E to the 2x multiplied by any constant c. Right? The only things whose derivatives are themselves are e to the x, or any scalar multiple of e to the x, right? Take the derivative of a scalar multiple of a function, it goes on for the ride. So any solution must look like this, where c is some undetermined constant, right? Because again, derivatives do not uniquely identify functions, but they do it up to a constant. So this here we would call a general solution to the differential equation, or if we're going to be really specific, a one-parameter family of solutions to the equation y prime is equal to 2y. Okay, great, wonderful. Now, we can expect that if you have more than one derivative, like a second-order linear differential equation, like this one right here, right, the order is 2, and the only operations affecting my unknown variable involve scaling, adding, and differentiation with respect to the independent variable. 2 derivatives means that we should expect 2 constants to show up. I claim that y equal to c1 e to the x plus c2 e to the negative x is a 2-parameter family of solutions. Right, now e to the x and e to the negative x, I didn't just pull these out of thin air. A couple of ways I could have gotten these, so later on we're going to talk about actual methods for creating solutions. But before we even do that, read this equation. Y double prime minus y equals 0. My function, its second derivative is itself. Clearly e to the x would be a candidate. And if you let your mind focus on it, you could probably also land that e to the negative x should work, because the chain rule would spit out a minus sign twice, so the minus signs would undo each other. Nice. Alright, so I claim it's a 2-parameter family of solutions, so here is the recognizing solutions, right? If I want to verify that this actually works, so my intuition tells me that this should work. E to the x obviously solves this from just reading the equation, and e to the negative x still should work. But if I wanted to really check it, let me take 2 derivatives. So there we go, I took 2 derivatives. Note, respecting the fact that when I take the derivative, a minus sign jumps out. And if I were to plug these into the equation, now here is where I'm talking about, this is the equation involving the unknown y's. Here's me telling you what y should equal. So what I'm verifying now is that if y does equal this, y double prime minus y will in fact equal 0. There we go, we see it right there. So there we go, I have verified that that is in fact a 2-parameter family of solutions, so I have a general solution to this second-order linear differential equation. Beautiful. Alright, cool stuff. Okay, well, got one more type of equation that we're going to look at. So when it comes to modeling physical phenomena, differential equations do a great job. And if you think about physical phenomenon, they're not isolated, right? When I drop my pencil, for the most part, it's just me dropping the pencil, but that could have some repercussions on maybe somebody who hears the pencil falling, or, things like that. Butterfly flapped its wings, and next thing you know, you're taking differential equations online in the summer of 2020. All right. So that means that we should expect several differential equations that occur simultaneously, and we call such a situation a system of differential equations. Okay, now for us, we're going to pretty much restrict our interest in this to the system of first order linear differential equations, so ones like this. So linear, because again, the only things happening are scaling and adding, and derivatives with respect to the independent variable. But now, if we read this, I've got two unknown functions, x and y, and they're intermingling with each other. So the derivative of x, the rate of change of x, depends on x itself and the function y. Likewise, the rate of change of y is dependent on y and the function x. So there is a commingling of my two unknown functions, x and y. In this case, again, we're using the Newtonian notation, so the independent variable has been obscured. Usually we'll use t for that. Now, I won't work out the details because it's very similar to one we just did, but this is in fact a general solution to the system. Again, two derivatives, two constants make an appearance. Even though a first derivative is the only one that showed up, there were two of them, so two constants, two derivatives. Seems like it's all lining up. Right, so on your own, you can verify this is a general solution by actually plugging it in and showing it does satisfy the equation they say it does. But, alright. So, now that we've seen, and it's worth noting, systems here, we won't talk about these until the end of the course, but we will get into these, but keep these in your mind. So now that we've seen this idea of a general solution, so given a differential equation, I can just basically give you anything that solves this is going to look like this, and there's this parameter that's showing up because, well, we're using derivatives, and derivatives do not uniquely identify things. If I were to give you some more information, though, I could uniquely identify things. So, for example, let's revisit our good friend y prime is equal to 2y. I know that anything that solves this is a scalar multiple of e to the 2x. So that means if I told you some more information about my function y, if I gave you some restrictions, I gave you some, bounding things here, I gave you some initial conditions, right? I'm now asking, I've got the function y whose derivative is twice itself, and at 0 it's equal to 6. Well, I can plug this into my general solution. E to the 0 is 1, so help you if you tell me that's anything else. I could solve and get you that c is equal to 6. So in other words, I can tell you the unique solution to the initial value problem, y prime equals 2y, y of 0 is 6. There's exactly one function in existence that's going to do this, and it's that one right there. Alright, so this is something we're going to be doing a lot in this class. So we're going to have differential equations, we're going to figure out how to get general solutions, and then we will usually follow that up with, okay, well now if you give me some initial conditions, what is the exact function that will work? So let's go to our favorite second order one that we just discussed, y double prime minus y equals 0, and let's say I give you two bits of information, one involving the function and one involving the derivative, and note that I'm talking about the inputs occurring at the exact same place, right? So what makes an initial value an initial value problem is that the input is the same always. If you have a second or higher order, you need to tell me derivative information. I wonder if we're going to have a lively discussion about the other types of value problems that are out there. Ooh, I don't know. Anyway, so here we've got a nice general solution to that, as we've already discussed. It's c1 e to the x plus c2 e to the x. So I have two unknowns and I have two pieces of information I can solve. Now, if I want to use this information I've been given, I'm going to have to take the derivative of this first. So let's go ahead and do that. There it is. And again, being careful about my minus sign making the jump out. Because now I'm going to plug in the initial conditions. I'm going to plug in 0 into y. That's equal to 1. Plugging 0 into this will eliminate the e terms, giving me c1 plus c2. Then I'm going to plug in 0 for y prime. That is equal to 3, giving me now c1 minus c2. So now I have two equations, two unknowns. However you want to solve this, the way I did it was I took the top equation and added it to the bottom one, and that gave me 4 is equal to 2c1, giving me c1 is 2, and then I plugged that one into the top equation, and then solved for c2, giving me c2 was negative 1, and thus 2e to the x minus e to the negative x is the unique solution to this initial value problem. Alright, well, let's start winding down here. So now that we've talked about the types of differential equations we're going to look at, the way solutions are going to present themselves, we now need to ask the two most important questions that you should always ask about any mathematical problem you're trying to attack. First off, can it even be solved? Do solutions exist? And then, if solutions are out there, how many solutions can you find? Okay. So you should always do this when you are doing any mathematical pursuit. Is there an answer? And how many answers can I find? And I'm not joking when I say that this is really the thing you should always do. Because one of the most famous unsolved problems in mathematics is solving the Navier-Stokes equations, which is a system of partial differential equations involving fluid flow. And to this date, existence and uniqueness is still up in the air. There's some special cases that have been figured out, but the overall full-out question, still unknown, and in fact, is one of the Millennium Prize problems, meaning that if you solve it, $1 million dues is your prize. And also, if you do solve it, if you don't have PhDs, if you don't have a PhD yet, the PhDs will rain from the sky on top of you. So go ahead and check that out. And again, note, it's a system of partial differential equations, so this could be well beyond anything we'll talk about. But it's worth noting that even now, in this most basic sort of math class, we're already getting close, right? We're touching these grand problems, these things that have been around for hundreds of years that no one's been able to figure out. So it's always a good thing when you reach that, that boundary point, that frontier of, right, you're getting there. We're getting to the cutting edge stuff. So, yeah, good stuff. And speaking of the Millennium Prize problems, only one of them has been solved so far since they were posed 20 years ago. So, yeah, they're not easy problems. All right. So, getting back on topic here, for us, what do we really need to care about when it comes to something like this? Well, it turns out we've got a nice theorem that tells us the following. Any first-order initial value problem, and every first-order initial value problem looks like this: a function of two variables on the right-hand side, the derivative of an unknown function y with respect to a variable x, and some initial condition given. If f and its partial with respect to y are continuous, then it turns out that there is an interval containing I, so that there is in fact a unique solution whose domain is at least I for my differential equation, satisfying my initial condition. Okay. So for us, what does this mean? This means that pretty much the reasonable first-order DEs, the ones that basically will naturally occur, the ones that we're mostly going to be focusing and working with, they'll have solutions, and furthermore, they'll be unique. Okay. Now, this is not to say that every single first-order differential equation has a unique solution. In fact, there's examples where they're not. You'll see it on WebAssign. But for our purposes, dragons exist, and good news, there's only one of them. But that still now begs the question of how do we go about slaying them? All right. Well, we've got all the terminology down. We got enough, I think, context for what we're going to be doing in this class. So, the next video, we're going to get right to it. We're going to start solving differential equations. Okay. So, we know what types of differential equations we're interested in. We know what we expect solutions to look like. And we now know that for initial value problems, I'm always going to be able to find a unique answer. Okay. So, we've set the stage. We've worked the plan. We've planned the work. I said it backwards. Damn it. We've planned the work, so now it's time to work the plan. All right. See you next time for the fun.